Last time I started talking about how we can better understand finitely generated modules over integral domains. For example, we proved that every finitely generated torsion-free module over an integral domain is a submodule of a finite free module. But today we are going to refine it further and show that in the case when the base ring is a principal ideal domain, our finitely generated torsion free is even free. So the first theorem that I'm going to prove is that if R is a principal ideal domain and M is a submodule of a finite free module, in this case, I say that we can conclude that M is also a finitely generated free module of rank at most M. The proof proceeds by induction on the rank of Rn. For the case when n is equal to 1, we only get an inclusion of 0 modules, and the empty set will be basis for both of them. And so we get that like rank of both of them is 0, and 0 is not greater than 0. When n is equal to 1, we get a submodule of a finite of the free rank 1 module. And any submodule of this form is an ideal. So M in R is an ideal. But R is a principal ideal domain. So M is generated by one element. And then either R is non-zero, and then multiplying every element of R by R, x goes to Rx, we get an isomorphism of R with M. And then M is a free rank 1 module, or R is 0, and then M is 0, and it is a free rank 0 module. So this was the base of induction. Now assume the case of n, and we want to conclude the case for rank of the free module, of the ambient free module, n plus 1. For this, I view M inside R n plus 1, and I say that R n plus 1 is isomorphic naturally to R plus Rn, and then I consider the projection pi onto the second factor, Rn. So here the n plus 1 tuple R0 through Rn goes to the n tuple R1 through Rn. And this defines a homomorphism, which I denote by pi vertical line m. So this is how we denote the restriction of a homomorphism to a submodule. And now I'm going to study its image and kernel. So first, the image of highly restricted to m is a submodule inside of Rn. So we are in the assumptions of this theorem, and by the induction hypothesis, image is a finite free module of rank at most m. By induction hypothesis, image of pi restricted to m is isomorphic to Rk for some k not greater than m. Now consider kernel of pi restricted to m. It consists of all elements of m whose first, second, and through n coordinates are equal to 0. So if we represent an element of m by this tuple, we want elements on the first, second, third, etc. through the nth place to be equal to 0. So this tuple should be equal to 0. So we only allow the first tuple, the first coordinate to vary. So we have that the kernel of pi restricted to m is equal to the intersection of m and r plus 0 viewed as a submodule in here, embedded using the first coordinate. So this is a submodule of r plus 0, but r plus 0 is naturally r. So kernel is a submodule of a rank 1 free module. So kernel pi restricted to m by the n equal to 1 case is finite free of rank 0 or 1. Okay, so we have that m via pi restricted to m surjects onto the image of pi restricted to m, but this is isomorphic to Rk. And on the previous lecture, we proved that maps from free modules, in this case we have a bijection from bottom to top, they lift against surjections. And we get that m is isomorphic to kernel of pi restricted to m plus Rk. So kernel is generated by 0 or 1 element and is free, and we add another free module. So m is also free. And it is of rank k if rank of kernel is 0, or k plus 1. But in either case, since k is at most n, k plus 1 will be at most n plus 1. And so we conclude the case for n+1, and we proved our induction step. And now combine this theorem with the fact from the previous lecture that every finitely generated, torsion-free, is a submodule of a finite free module, and we get corollary 1 that over a principal ideal domain, every finitely generated torsion-free module is free. And corollary 2, over a principal ideal domain, consider a sequence of inclusions of modules. So a free module of rank n is injected into M, and M is in turn injected into Rn. Injective homomorphisms of R modules. So in case we have this tower of inclusions, then we can conclude that M is itself a rank n free module over R. To make it clear, M is a submodule of Rn. So by this theorem, it is finite free of rank at most n. So M is free, and rank M is at most n. And now, using the first inclusion, we get that Rn is a submodule of a finite free module M. So by this theorem, the rank of Rn is at most rank of M, which was at most M by this inequality. And so we conclude that the rank of M is equal to N, which means that M is isomorphic to Rn. This is what we claimed. Let me show you how all of this can be false over non-principal ideal domains. So, non-examples. First, if R is not a principal ideal domain, then this theorem is always, absolutely always false. Because we either have that R is an integral domain with a non-principal ideal, non-principal ideal I inside of R, and in this case I is a submodule of R, and I is not free, or R is not an integral domain, in which case we can find 0 divisors xy is equal to 0 such that both x and y are non-zero. And then the ideal generated by x is a submodule of a rank 1 free module, but it is not free. Because, for example, element x gives a set that is not linearly independent, with the non-trivial linear combination being y is equal to x, and it is equal to 0. Okay, so corollary 1, if we consider the ideal of the ideal generated by x and y inside C adjoin x and y, then it is not free, although it is finite and torsion free. And moreover, I can continue it into a counterexample for corollary 2 by sending C adjoin xy in x comma y, and f goes to x times f, which is an element inside the ideal. And the ideal itself is inside C adjoin x and y. And this ideal is not isomorphic to R, because it is not, for example, generated by one element.